Okay, so now that we understood how slip velocities or slip length can have a great impact on the motion of fluid elements at length scales that are comparable to the thickness of a solid-liquid interface, I want to come to the field of interfacial transport. And an interfacial transport is a rather broad field which includes all forms of particle or fluid motion that is driven by the coupling between the liquid and solid phase within an interfacial layer. In my opinion, the best way to rationalize each problem is to go through the following 4 steps. As a first step, we need to identify the type of external fields which surrounds a solid wall or a solid particle, and that leads to fluid motion within the interfacial layer. And this allows us to distinguish between essentially transport in electric field, transport in chemical gradients, and transport in temperature gradients. The second step consists in locating the interface and its thickness. So it consists in figuring out up to which distance lambda the coupling between the fluid medium and the solid surface is important. Then, as a third step, we need to understand which boundary conditions we are dealing with. So here, whether we are considering the fluid motion around a fixed surface, and in this case we talk about osmosis, or whether the solid phase is free suspended, as in the case of particle, and here we talk about phoresis. Then the final and most important step is to calculate or at least estimate the slip velocity and its direction, as well as any corresponding mobilities of particle. Okay, so now let us begin with transport of fluids or particle when an electric field is applied in one direction. Here, for example, we can use 2 electrodes and apply an external electric field in the x direction, and consider a solid particle or a solid surface that is immersed in water in between. This solid surface of the particle carries a surface charge, which here you can think, for example, of common glass, which in water ionizes to produce Si or minus groups. However, this charge is typically neutralized by the counter ions in solution. So in principle, under the applied external electric field, there's no net force, and as a result, no net motion is expected. However, if we look closer, our neutrality is lost in the interfacial layer, since our ion distribution always gather around a charged surface. And this brings us to the second step, which is to figure out what are the relevant landscape of this ion distribution. And in particular, the charge profile includes a large number of length scales. However, most of them are in the range of fractions to few nanometers, and are often much smaller than the almighty debye screening length, which often goes up to hundreds of nanometers. So, ubi major minor cestet. As a result, our debye length describes well enough the diffuse clouds of counter ions near a charged surface, and as I'm pretty sure you know already, is the characteristic length of the exponential decay of the electrostatic potential, as shown here. This is valid if we exclude what happened very close to the charged surface. Now, step 3, as I mentioned a few times already, is where we need to distinguish whether we hold the solid substrate, so we fix the velocity to 0 at the solid wall, or whether we hold the fluid far away and we let the solid surface free to move, as in the case of phoresis of colloidal particles. And the last and most important step is to calculate the slip velocity. And here we begin with the case of electrosmosis, in which we deal with a fixed charge substrate and apply an electric field parallel to it, and call UZ the velocity profile in the perpendicular direction. So here the force balance, or Stokes equation, tell us that the sum of the viscous friction force and the electric body force has to be equal to 0, where here eta is the fluid viscosity, and C plus and C minus is the concentration of positive and negative ions. This concentration of positive and negative ions are linked to the electrostatic potential through this Poisson equation. So, in short, by combining these two equations and integrating twice, we are able to obtain the velocity profile, which looks like this, where this eta is an integration constant. Sorry, where this zeta is an integration constant. Finally, our slip velocity is defined at the outer bound of the interfacial layer. And this means, strictly speaking, it is defined at z equal to infinity, since the electrostatic potential is an exponential decay. However, in practice, it is defined somewhere after the device spinning length. And our electrosmotic slip velocity is proportional to the external electric field, where this zeta is equal to the surface potential in order to satisfy the boundary condition that the velocity has to be 0 at the solid surface. So, in conclusion, due to electrosmosis, fluid is driven in the direction opposite to the external electric field if the surface potential of the substrate is positive, and the other way around if the substrate is negatively charged, as shown as in the case of this sketch. Then everything is very similar if we deal with electrophoresis instead of electrosmosis. So in the case in which we are considering a freely moving substrate or particle, except for the fact that the integration constant, the Z, is now equal to the electrostatic potential at infinity in order to satisfy this other boundary condition, that we are holding the fluid far away. And also the sign of the slip velocity changes. So as a result, due to electrophoresis, positively charged particles migrate in the direction of the external electric field, whereas negatively charged particles are driven in the direction opposite to the electric field due to electrophoresis. So at this stage, I think it is useful to say a few more words about this integration constant, zeta, which is also known as the zeta potential in the context of electrophoresis. On one hand, this zeta gives the electrophoretic mobility of freely suspended particles. So essentially the proportionality between the slip velocity and the external electric field. It is what instruments like a zeta sizer returns as measurement outputs, where they apply an external electric field. They measure the velocity of the particle under this applied external electric field, and as such, they extract the mobility. And for colloidal particles, zeta is in the range of 0 to plus or minus 100 millivolts, either for positively or negatively charged particles. On the other hand, zeta is also the value of the electrostatic potential at the outer edge of the interface, as I mentioned before. So strictly speaking, at zeta equal to infinity, but in practice somewhere after the Debye length in a region which is called the slip layer. It is very important to keep in mind that this zeta potential cannot be used to extrapolate the surface potential of the particle, since the exponential decay is no longer valid near the solid surface, where the distribution of ions is much more complicated. So here just important, you should not remove this tag and keep in mind what a zeta potential really is. So far, we also have assumed that both the electric field and the zeta potential are constant in the direction parallel to the surface. However, let's now consider a situation in which a surface is patterned with bands of positive and negative charge density. Well, in this situation, the electrical mobility varies in x, and this leads to a gradient of pressure and recirculating rolls with fluid that enters and leaves in the direction perpendicular to the surface. And this is nicely shown in this video here, or as well as in this article. The same thing happens if we have a conductive surface or a conductive particle, which acquires an additional zeta potential under an applied external electric field. This is known as induced charge electrosmosis or induced charge electrophoresis, and sums up to classical electrosmosis or electrophoresis, leading to an additional slip velocity. This additional slip velocity is proportional to the electric field square, since an object of size r, say, roughly gains, under an external electric field, roughly gains a zeta potential, which is of the order of E times r, so that essentially if you go back to this equation, you have that r times c, you have E squared. So in conclusion, since the slip velocity due to induced charge electrophoresis scales as e to the power 2, while the slip velocity due to classical electrophoresis is linear with the external electric field, often in experiment, the dominant effect is induced charge electrophoresis or induced charge electrosmosis, since this scale becomes dominant as soon as the electric field is large enough. I'm still talking about experiment. A DC electric field such as those we have considered so far are much more complicated to use than oscillating electric field. This is because Faraday reaction often happen across the electrodes, and because the electric field that are needed are often not strong enough. However, according to what we said so far, AC fields are kind of hopeless, since they will always produce a zero-time average flow if the induced electric double layer builds up entirely. However, if the electrical double layer builds up entirely is often not entirely true, or is often not entirely the case. In fact, the formation of an induced spinning layers always takes some time, so that a net flow is effectively obtained as soon as the electrical double layer only builds up partially. And here one can model the formation of an induced charge slippage using an RC circuit. This is a very smart way to model, of capacitors of thickness lambda and charging time tau c, where this tau c is proportional to the size of the object and to the device spinning length, and is inversely proportional to the diffusion coefficient of the surrounding ions. In other words, thicker interfaces, which are made of slow ions, take a longer time to form. So as a result, when the operating frequency of the AC electric field is smaller than the inverse of this charging time tau c, then here we have a full build-up of the electric double layer, and therefore we have a zero time average flow. On the other hand, induced charge electrophoresis and induced charge electroosmosis worse in AC field if the operating frequency is larger than this tau c to the minus 1, but at the same time it has to be not too large so that our electric double layer doesn't build up at all. This second condition also set on upper critical frequency, which is the inverse of the Brownian diffusion time of ions across the interfacial layer. So it's equal to the diffusivity of the ions divided by the Delaunay length square. And we will see soon that these timescales are very important when it comes to the fabrication of synthetic microstreamers in AC electric fields. However, before moving to active matter, let's see first what happens when the particle or the substrate are immersed in a concentration gradient of solid molecules. Here, even neutral molecules can show a degree of affinity with a neighboring solid surface, so that although at the microscopic level there's no net force acting on the particle, these local affinities are able to lead to osmotic pressure gradients in the interfacial layer, and therefore to a net flow. As a second step, we need to identify what is the relevant solid-liquid interface and its thickness, as we did in the case of electroosmosis and electrophoresis. This is the layer where the solid-surface interactions, including extruded volume interaction or van der Waals forces or London forces and so on, play an important role and give rise to a local absorption. For this reason, we call this interface the adsorption layer, and label its thickness with the symbol lambda, which I want to point out is no longer the Debye length, although I decided to keep the same symbol for consistency in order to denote the thickness of the interfacial layer. This adsorption layer is rather complex. However, we are lucky because most of the physics can be understood simply by simplifying the problem as if there's no adsorption at distances from the solid surface that are larger than lambda, whereas there is adsorption happens when the solutes are at distances from the surface that are smaller than lambda. The third step, following our protocol, is exactly identical as in the case of electrophoresis and electroosmosis. So where we have diffusiosmosis in case we hold the substrate, whereas on the other hand we have diffusiophoresis if we have a freely suspended surface or freely suspended particle while we hold the fluid far away. Okay. As well as before, we begin with the case of diffusiosmosis and consider two neutral solids, say 1 and 2, which have a binding energies A1 and A2 with respect to the fixed substrate. So the concentration of 1 and 2 increases and decreases along the x direction as shown in the sketch here. So in this problem, if we are far away from the surfaces, so at distances that are larger than lambda, the osmotic pressure has to equilibrate, so this P is constant along x, where C1 and C2 are the concentration of the species 1 and species 2 in bulk. On the other hand, if we are at distances that are smaller than lambda from the solid surface, then the interfacial layer feels a gradient of osmotic pressure, which is a function of the position x. And this gradient is given by the absorption probability of the species 1 and 2, respectively. This gradient of osmotic pressures always follow the gradient of concentration of the favorite solute. Since this prefactor is positive if the binding energy of 1 is larger than the binding energy of 2, and is negative the other way around. So in other words, the gradient of osmotic pressure follows delta C1 if the first surface prefers 1, and the gradient of C2 if the surface prefers 2. Then the force balance is fairly simple, or Stokes equation is fairly simple. It is the sum of viscous friction and the difference of osmotic pressure. So that after integration and imposing the fixed surface boundary condition as we did before, the slip velocity, which I remind you is defined at the outer bound of the interfacial layer, so here at z equal to lambda, is equal to minus lambda squared divided by 2 times the viscosity of the fluid times the gradient of osmotic pressure. So the diffuser osmosis leads to fluid transport in the direction of the least favorite solute because of this minus sign. The case of diffusophoresis is identical except for the different boundary condition of fixing the fluidified away rather than fixing the substrate. So it leads to a slip velocity with the opposite sign, so that a diffusophoretic migration occurs always in the direction of the favorite solid. And I summarize this in this table over here. Okay, so what we've seen so far is only in the case of neutral diffusophoresis where the solute carries no charge. However, if the particle or the substrate is immersed in a solution of electrolytes, which is a very common situation in experiments, things becomes a little bit more complicated. Since here the slip becomes the sum of the neutral diffusophoretic contribution, here on the right, and an electrophoretic contribution, since gradients of ions also establish a local electric fields. So here both these two terms scales as the gradient of the log of the concentration of salt in bulk. And I just want to justify this qualitatively with few scaling arguments. On one end, if we look at the diffusophoretic slip velocity, we've seen before that this is proportional to the thickness of the interfacial layer square times the gradient of concentration in bulk. So here now we are dealing with ions. So the thickness of the interface, we are now back to the device screening length, which is proportional to 1 over the square root of the salt concentration. So that if we put these two together, we obtain that the diffusophoretic slip velocity increases linearly with the log of the bulk salt concentration. On the other hand, the electrophoretic term is proportional to the zeta potential of the particle times the electric field, which now is the electric field that is given by the distribution of ions around the particle. And so it depends on how mobile are the cations and the anions. And it's also proportional, again, to the gradient of the log of the salt concentration. This is qualitatively understood if we consider that the electric field is the gradient of the electrostatic potential, and the concentration of positive and negative ions is linked to the electrostatic potential by the boson distribution. So if you put these two together, you obtain this. So here we have that Both terms are proportional to the gradient of the log of the salt concentration. And how about the direction of the slip velocity? Well, in case of the diffusiophoretic slip velocity, it always follows the direction of the salt concentration. So the particle always migrate up the concentration gradient, as we've seen before. And here we only have one solid. On the other hand, the electrophoretic slip velocity, its direction depends on the direction of the local electric field, which goes this way if the positive ions diffuse faster than the negative ions. And here you can think of these red circles, which are moving faster in this direction, so that we have an excess of positive ions, of positive charge on this side, and an excess of negative charge on this other side. Whereas it's the opposite if the negative ions are faster than the positive ones. So all in all, the electrophoretic slip velocity can either go in this direction or this other direction, depending on the sign of the zero potential, and depending on whether the positive ions diffuse faster than the negative ions, or vice versa. And here is a nice experimental example of what we just said, where in this experiment the authors use polystyrene negatively charged particle, so with a negative zeta potential, and apply a gradient of salt along this direction. So here they tested two salts. On one end, caustic soda, NaOH, where the anions diffuse faster than the cations, so that the direction of the electric field is opposite to the one of the salt concentration gradient. So here it means that here both the electrophoretic slip velocity and the neutral diffusiophoretic slip velocity point in the same direction, and therefore the particle always move up the concentration gradient. On the other hand, on the right-hand side, if we use hydrochloride salt, where H plus cations are faster than the anions, then here we have an electric field which goes this way, and therefore an electrophoretic slip velocity which counteracts the diffusiophoretic slippage. And since the magnitude in this particular experiment of this term is larger than the magnitude of this term, we have a net migration of the particle toward the region of low salt concentration. So experimentally, all these concentration gradients are typically obtained in microfluidic devices, such as this one illustrated in these two pictures, where the colloids are injected in the central channel, while a solute comes from two side channels, so that our colloidal suspension either spread out or is focused toward the center of this channel, depending on the sign of its phoretic mobility. An alternative way is to employ permeable membranes or permeable walls, so that in this way we are able to flow on one side the ice water and set to zero the concentration of salt, for example, at this wall, whereas on the other side a controlled concentration of salt flows through this other left channel. So here we have a well-established concentration of salt in this direction, and particles migrate either this way or this other way, depending on the sign and the magnitude of the neutral diffusiophoretic and the electrophoretic mobility. Okay, so we now come to the last form of interfacial transport I want to talk about today, which occurs in the presence of temperature gradient which surround a particle or a fixed substrate. These phenomena are known as thermosmosis and thermophoresis, where again the difference between the two is just given by the boundary conditions. However, the physical origin of transport in thermal gradients is not as intuitive as in the case of an applied external electric field or a surrounding concentration gradient of solid molecules. So here perhaps the best way to understand why particle or fluid elements move in temperature fields, even though there is actually no net force acting on the particle, is to recall the Osnager reciprocal theorem, which states that the heat flow per unit of pressure difference and the density matter flow per unit of temperature difference are equal. This means that within an interfacial layer there is a strong correlation between the slip velocity under an external temperature gradient and the slip velocity that would occur if a concentration gradient is applied instead. So in particular, given this property of reciprocity and following our four-step protocol, we can claim that the interfacial layer responsible for thermophoretic or thermosmotic transport is the same adsorption layer which we have used for in the case of diffuse osmosis and diffusophoresis. And we can also claim that the slip velocity is now no longer a function of the osmotic pressure difference, but it's related to the excess or deficiency of enthalpy carried by an equivalent pressure-driven convection fluid. And this approach leads to the following two expressions for the thermosmotic and the thermophoretic slip velocity, where this H is the excess or deficiency of enthalpy at the surface, and where the osmotic flows actually follows the direction of the thermal gradient if this H is negative, which is actually the most common situation, whereas on the other hand, thermophoretic drifts occur towards the cold region, again if H is negative. However, I went rather quickly through this form of interfacial transport, since actually this framework is very complicated. And it is very complicated because of two reasons. On one hand, it is very difficult to measure H experimentally. So it is very difficult to measure what is the excess or deficiency of enthalpy. And on the other hand, because the thermophoretic mobility, as you can see in this formula here, is now a function of the temperature. So for these two reasons, it is often more useful to characterize the thermophoretic transport of free suspended particle using a different approach, in which we consider a suspension of colloidal particle on mean number density n and monitor the concentration profile when a temperature gradient is applied along one direction, say along x. So here we can write that the total mass the total mass flux is the sum of a diffusion term and a thermophoretic migration, where here this mu Tp is the thermophoretic mobility of the particles. If now we impose a zero max flux, we see that the SRA coefficient, which is defined as the ratio between the thermophoretic mobility and the Brownian diffusion coefficient of the particle, is measured by looking at the density profile along the direction in which the temperature gradient is applied. Where here, by definition, the SRA coefficient is positive if the particles migrate towards the core region and is negative otherwise. This approach is kind of analogous to what people do when they deal with a colloidal suspension under real external fields, such as, for example, under gravity. Where here one can define a gravitational length as the ratio between the diffusivity of the particles and the sedimentation velocity, and say that if this gravitational length is much larger than the typical size of the colloids, then the dynamics is governed by diffusion. Whereas if the gravitational length is much smaller than the size of the particle, sedimentation dominates. And here the same can be done in the case of a thermophoretic drift, where one introduces a thermophoretic characteristic length scales, and says that if this length scale is much larger than the size of the particle, then the dynamic is governed by diffusion, whereas thermal transport towards the cold or the hot region is dominant if this length scale is much smaller than the size of the colloids. Finally, very briefly, how are thermophoretic experiments typically done? A first approach is to use microfluidic devices that are pretty similar to those we have seen in the case of diffusiophoretic and diffuse osmotic transport, where instead of having a reservoir of salt, we have two sides which are cold and hot respectively. And here we have an inlet where the probe colloids are injected, so that a migration either towards the cold or towards the hot happen in the direction normal to the channel length. Alternatively, one can use a light absorbing material, such as gold nanoparticles, and illuminate it with a laser beam so that a thermal gradient is obtained radially in this direction. So in this particular case, this method has been used to study the thermosmotic flow when this light absorbed particles is stuck to one of these channels molds. A similar experiment, but for the case of thermophoresis, has been done by optically trapping a light absorbing colloid and look at the migration of surrounding microparticle under this three-dimensional point-like source, where in this particular example, we have a migration of the particle towards the hot region, so that in other words the particles have a negative Fourier coefficient.